Okay, kids, 3U assignment, chapter 4, question 12. So let's see what information we've been given. Let's see what information we've been given. It says an archer knocks a 0.20 kilogram arrow on a bowstring. So the mass is very important here. Mass is 0.20 kilograms. The archer exerts an average force of 110 newtons to draw the string back 0.60 meters. Let me explain what they mean by that. So I don't know if anyone, I think they do archery in gym class, don't they? Haven't they done that in past years? Maybe last year, 2 years ago? I thought they did. Okay, that's all right. So here is the bow and the string. And then what you do is you put an arrow in here, right? And then what happens is with your hand, you pull this back, right? And they tell you that you pull it back with a force, and let's just call it force P for pull, you pull it back, of positive 110 newtons. And we know that when you pull it back, the string will now be here, right? So you pulled it back a certain displacement. And that displacement that you pulled it back, we know will be a displacement of positive 0.60 meters. And we're going to assume that friction is negligible. Okay, so then what happens is the person pulls the arrow back on the string, and then for an instant, the arrow is not moving, right? And then the person releases the spring and the arrow so that this arrow starts to fly off. So now this arrow leaves the bow and the string. So we want to know what is the speed of that arrow. So there's your required. What is the speed of the arrow when it leaves the bow and string? Now remember, kids, we are in the energy unit. So I don't expect you to use kinematics equations. As a matter of fact, if you use kinematics equations, you're not going to get the marks. This is the energy unit. I've already tested you on dynamics and kinematics. I'm testing you on energy methods. So be aware of that. Yeah, don't start using all that kinematic stuff I taught you. That's already been assessed on an assignment. This is energy. So when the person pulls on the string with the bow and the arrow, that person is doing work, right? And you know how to calculate work. I don't want to give the question away, but you know how to calculate work, right? The work done by pulling the arrow. Because look, you know how far it was pulled, and you know the force that was used to pull it. So there's an equation that is going to allow you to calculate the work. It exists. I'm not going to tell you what that is because this is an assignment. Now, one of the key points of this chapter is this following an equation. I will give you this. Whenever you do work on an object, and there was a video lesson about this, okay? Whenever you do work on an object, you are giving that object energy. So if you calculate the amount of work done on this object, you would have calculated how much energy has been given to that object. And in this particular case, in part A here, the amount of energy that's been given to it, or the kind of energy that's been given to it, is kinetic. So really, if you think about this, this would be kinetic energy final minus kinetic energy initial. That's what delta means, right? But kids, how fast is the arrow moving just as it's being released? At the very beginning, how fast is it moving? Just. How fast? Yash, what do you think? No, like I just released the arrow. How fast is it moving? Just is the key word. 0. Okay. As I just release it, it starts from 0 and then it flies off. So this is gone. Right? So that means I know how much work was done. I know that work gave the arrow kinetic energy. I know it started with no kinetic energy. Is there an equation out there that links speed and kinetic energy? Yes, there is. There is. So this is part A for this. Part B, you do the same thing, except the arrow is shot upward. Okay? The arrow is shot upward. So now I have a different given diagram. Okay? The arrow is shot upward, and then the arrow gets to what we call its high point. Okay? It doesn't get any higher than this. So when it gets to this point here, the highest it's going to get to, its speed right there, because you know what happens to an object when it reaches its highest point. How fast is it going? When it reaches its highest point, 0. Whenever something's thrown in the air, okay, I'm in class here with the kids. Watch this. It stopped for an instant. So when it gets up here, it's not moving. But the bow and arrow still did work on it, right? The same work that it did from part A. But now, instead of looking at this as I've given it kinetic energy, I've given this arrow a displacement, which is a height. I've given it height. I've changed its position in the gravitational field. So now work is still change in energy, yes, but the change in energy now is no longer kinetic because it's not moving up here. Look, it's not moving. So all of the work when the object is at the height of its motion has gone into gravitational potential energy. It's the same amount from part A, but it manifests itself as height, as gravitational potential energy. All right? And you know what delta means? Final minus initial, right? We can assume, for the sake of argument, that right here, when the arrow started, that its height was 0. Okay? So if an object starts with a 0 height, or its initial height initial, right? Its initial gravitational potential energy would be 0. What's the equation for gravitational potential energy? Think about it, right? If you've got 0 height, you've got 0 gravitational potential energy. So now the question becomes, okay, I know how much work I did. That work changed the gravitational potential energy. But I started with no gravitational potential energy, so that means, in essence, I know this. The gravitational potential energy of the arrow when it's at this point right here, where it's got no velocity, no speed. But I want to find that height that it has achieved. I want to find that height. Is there an equation that will link gravitational potential energy and the new height achieved by this object? Does such an equation exist? I bet you it does. So kids, we are using energy methods here. We're not using kinematics dynamics. I won't give you the marks. I simply won't. Is this helping? Justin? Is this good? Up or down? Is this good? You're going to have to be louder. You got a mask. I'm old.
I will think about it.
You will think about it. I love that answer. I will think about this. Perfect. That's what I wanted. I wanted you to think about it. Okay?